Alright guys, welcome back. In this video we want to use the force method to solve this statically indeterminate problem, which is 1 degree statically indeterminate. And we can figure that out by counting up the reactions. We have 3 at point A, we got MA at the moment, and then we got AX and AY. And then we got 1 reaction over here at B, which is just a vertical force, so we got BY. So we have 3 equations of equilibrium available to us in this problem, and we have 4 unknowns. And so basically we have 1 too many unknowns and we can't solve it with statics alone. So just because we have 1 too many, that makes it first degree statically indeterminate. If we had 2 extra unknown forces, then it would be second degree statically indeterminate. So for problems that are just 1 degree indeterminate, force method is pretty good for us to use because we're just going to get a single expression with a single unknown. For problems like you'll see in the next video with more than one degree of indeterminacy, typically force method is like not the most efficient way. Often, sometimes it could be, but like you're better off usually using 3-moment equation or what's that other one? Slope deflection method. That one's a pretty good one too. So, anyways, moving forward with this 1 degree statically indeterminate problem, basically you have to pick one of the reactions to basically define as the redundant reaction, and this is just what we're going to be separating out from the rest when we're doing the principle of superposition. If we have a cantilever beam with like an extra support, then often it is easiest just to call this one the redundant reaction that we're going to be working with. So basically we're going to remove this from the beam. So let's actually do that. Let's just draw the beam here with only the applied loads. And when we remove this BY reaction, then this system basically becomes a statically determinate problem because there's just 3 unknown reactions at A. And that's it. And so we can easily solve this with statics. But what we're doing when we do this is we're using the principle of superposition, saying that the original system with all of the applied loads plus the redundant reactions is equal to the system with the redundant reaction removed, reaction if there's only 1 or reactions if there's more than 1, plus the system where we just have basically that unknown force acting on it. And the comparisons really that we want to make here is in the deflection. So we want to say that the actual deflection of the loaded structure with the real supports and everything is going to come out something like this. So it'll be 90 degrees coming out of the wall because that's a rigid connection. It's going to dip down and it's going to come back and have 0 deflection right here because the support isn't being pushed into the ground or anything like that. So this deflection is equal to the superposition of these other 2 deflections, right? So this one where we have these loads is going to be bending us down something like this. And if we call this case 1, then this deflection here is just going to be called, we can call that Y1, right? Just the deflection due to the applied loads. Now if we call this case 2 down here, then what we can do is if we just applied the point load BY, which is the actual magnitude of the reaction, but it's an unknown, that's fine, then we're going to get some deflection here, and we're just going to call this Y2. And so we know that this upward deflection caused by the redundant reaction, it has to be equal and opposite to the downward deflection here caused by the point loads, because in real life, or in the real situation, or the real case, the point here at B has actual 0 deflection. So what we can say is Y1 plus Y2 is equal to 0. All right, so let's not forget that Y1 is going down and Y2 is going up. So really, when we look at this, I'm going to use tables for this. What we can do is we need to generate an expression for the deflection at point B. You can do this using the moment area method. You can do this using the double integration method, or you can use this using you can do this using tables as well if they're available to you. So if you come check out a table like in the back of your textbook, or I have one on the website that's right here. URL's up here if you want to grab it. Otherwise, you can just just check it out in the video. I've kind of referenced this in a couple other videos as well. Basically, when we're looking at the applied loads on our beam, or in this case 1, there's 2. There's the distributed load, and then there's the point load. So actually what we need to do for the deflection Y1, this is also a superposition problem, which is the deflection on a cantilever beam with just a distributed load, plus the deflection of a cantilever beam with just a point load acting at the end. And we got both of those cases right here. So this one is for the deflected load, and the distributed load, and this one is for the point load right at the end. So the deflection here is negative WL fourth over 8EI. This negative indicates it's basically going to give us a downward deflection. And for the point load, we have y equals negative PL cubed over 3EI. All right, so let's go and drop those as what we got for y1. So we have negative WL to the power of 4 over 8EI. And that was minus PL cubed over 3EI. All right, so that is, again, that's the superposition of the distributed load, which is this guy, this term here, and also the point load acting at the end of the cantilever beam, which is this guy here. Now what we have to do is we add in our expression for y2, and y2 is also a point load. But it's a point load at the end of a cantilever beam, and it's going upwards. So basically, it's just this exact same term, just with a positive sign. So plus PL cubed over 3EI. Now, obviously, this W refers to this distributed load. This P refers to this point load, and this B refers to this unknown force By. So let's maybe we should update some of those. Let's set this all equal to 0. What we can do is we can actually split these onto different sides. So we'll bring all the stuff over to the other side, and we can write this just as By. What was L? I don't think I defined L. Let's go actually. Let's say that L was equal to 2 meters. I think that will be a good example. Probably should have written that on from the beginning of the problem. L equals 2 meters. All right, so we got By times 2 meters cubed over 3EI. And then we're going to bring all this stuff over to the other side. So we had, this all becomes positive, and this was 10 kilonewtons per meter. We can write in the units if we want, kilonewtons per meter times 2 meters to the power of 4, all over 8EI. And we had plus this P, so this is 50 kilonewtons times 2 meters squared, 2 meters cubed, and that was all over 3EI. All right, what we can do is we can we can multiply both sides of the equation, each term by EI, so that's going to reduce a little bit. And then we can divide each term by actually 2 meters cubed, and these are going to drop out, and this is just going to be reduced to 2 meters. So we're basically just going to be left with By over 3 is equal to 10 kilonewtons per meter times 2 meters. This is all over 8, and plus 50 kilonewtons over 3. All right, so we can just rearrange that just a little bit. We get By is going to be equal to 3 times 2.5 kilonewtons plus 16.667 kilonewtons. And we're going to find that By is equal to 57.5 kilonewtons in the upward direction. So that's pretty cool. We actually just solved for By. And basically, in this part here where we have this equation, this is our one equation with one unknown. And the only unknown in this is By. And we're able to figure out what By is because we link these two together knowing that there's 0 deflection. So it's not the deflection that's unknown, it is the magnitude By, which is the unknown in this expression. And from here, now that we have By, what we can do is we can just do like the sum of forces in the y direction on the overall structure, now that we know that By is equal to 57.5 kilonewtons going up. And so basically we have that Ay is equal to 12.5 kilonewtons going up. So we got Ay here, we can label this on, we have 12.5 kilonewtons going up. Ax here, well, Ax is the only horizontal force, and so this is going to be equal to 0. We don't really need to do anything fancy there. And then just to solve for the final reaction here, this is Ma is going to be 5.6 kilonewtons, and it's a positive value, so the way that we drew it, with the way that we assumed, turned out to be right, so we can write this on here. Ma is equal to 5.6, not kilonewtons, kilonewton meters. 5.6 kilonewton meters. All right, so there we go, guys. We solved for all of the reactions on this statically indeterminate problem that was 1 degree indeterminate using the force method.